Okay, let's start our second talk by Professor Seokcheon Lee, and he will continue his talk, his first lecture. And today he will mainly talk about CMB and BAO. Yes, I think. Okay, you may start now.
Okay, yeah. Okay, so thanks for coming again. And then, yeah, today we'll talk about the CMB and the large scale structure, especially focused on the BAO, but BAO is actually same as the CMB. So after you understand the mechanism for the CMB, BAO can be understood. And for the BAO is just a part of the small part of the power spectrum. And as Stefan emphasized in the real observation, the calculation is quite simple based on the dark matter. But what we really observe is the galaxy, which is a baryon. So there's the bias factor problem and the peculiar velocity motion, and also the line of sight, the observation problem. So it's so-called as a red space distortion problem, etc. So in reality, in the observation is more complicated. But today, what I want to try to explain is a more theoretical prediction, how to obtain the CMB and the matter power spectrum based on our simple inflation model. So all the details is actually Stefan already covered very nicely. So let me just introduce what I need to do today is just a theory about how we can understand the peaks in the CMB, and from those things we need to interpret the cosmological parameter from the feature of the power spectrum. So that's the main focus. And then also as a standard rule, BAO is focused very much. But the thing is that this is a galaxy. So the bias factor problem is always there. And it's not clear actually how they use the bias factor to characterize the BAO. BAO is actually in the configuration space is one single epoch, and its size is just the distance to the last scattering surface. So it's about 100 megaparsec. But when they converted it to the Fourier mode in the K, then there's the wiggle shape due to the Fourier mode. So this kind of, if B bias vector have the K dependence in the interpretation in their galaxy, then it's really difficult to have because we need to worry about the amplitude problem, not only as a standard ruler as a distance, but wiggle problem is actually also including the amplitude, which is also related to the bias vector. So it's very complicated. So let me just briefly mention that the problem is the Einstein equation is just this, but we assume that the background is a cosmological principle as a homogeneous and isotropy, which is about good at about 300 megaparsec. Then we assume that the metric itself is averaged as a homogeneous and isotropy. But that really means Einstein equation can be averaged. Because on the right-hand side, we can do that. We usually do that. We do the thermal averaging. But right-hand side, we derive the Einstein field equation from the averaged metric. But that doesn't really mean that the average of the curvature is another issue. But yeah, also, so we can think about the anisotropy model and then inhomogeneous model, so-called as a Lemaitre-Tolman-Bondi model or Bianchi model. But CMB already ruled out this one, almost at the 10 to the minus 5 level. But LTB, if you adopt this one, some people can say that the local motion looks like accelerating, but globally it's not necessarily accelerating phase. So one can escape from the dark energy problem. But then the problem is that if we are living in those specific area, appear to be accelerating due to be close to the void region. Then we cannot say anything about the global structure of the universe. So LTV can solve for the local problem, but in the overall size, we cannot say anything. We should specify the metric depend on the scale or location. So even though it can be alternative solution, but it cannot, one can say that, but it's not adopted as a global solution. And dark matter and dark energy is also troublesome, and so some people try to use the MOND for the explain the galaxy cluster. In the large scale, Newtonian dynamics is different from the 1/r square force, or TEVIS is a relativity version of the MOND, including as a propagator, not only tensor as a graviton, but people can have the vector and scalar. Scalar and tensor is usually Franz-Dicke theory. Vector means we can also including the repulsive force, which acts as the dark energy in some sense, or repulsive acceleration, repulsive forces. So it can replace the dark matter problem. But the problem is nowadays, or as Stefan already told us, that without dark matter, large scale structure cannot be explained. The growth is only dependent. If a baryon is only the one, then it grows as a scale factor after the last scattering, but it's only grow about 10 to the 3 from the last scattering surface. But in order to explain grow from the 10 to the -5 to the order 1 at today, then we need 10 more time. And which can come from if dark matter is already grown up without any interaction with the photon, then that can overcome this one, and baryon catch up the growth of the dark matter. So dark matter is really necessary to explain the CMB and large scale structure. But the dark energy part is sometimes it's better to replace it by MOND, because dark energy usually limited by the equation of state, cannot be smaller than -1. But maybe Stefan told us that some supernova data prefer the phantom region, which means it's a equation of state can be even smaller than -1. Then usually dark energy model cannot explain that theoretically, except to violate the energy condition. But dark modified gravity is an effective equation of state. So it can naturally have the smaller than -1. So dark energy part is still arguable with the modified gravity. And in order to explain that one, usually the F sigma and sigma observation is expected to be explain that problem. Okay, so observable is quite complicated, and the details is in the devils is in the detail, which is actually told by the Ludwig Leho. He's actually he's an architecture, not a scientist, but he say the God is in the detail. He actually very accurate in his structure architecture. So he even controlled the nut and used in his building. So it's the guy who's talking about this one first. And as you can guess from his name, he has the same name as the Beethoven, and same name. And I just checked, the Ludwig means the famous warrior. The meaning in German means the famous warrior. So every detail is actually, as you already seen, is in the transfer function. Our observable quantity doesn't matter, it's matter fluctuation or the photon fluctuation is originated from the curvature perturbation due to the Einstein field equation. And then because the metric is connected to the matter part. So right-hand side term is just connected by the left-hand side term. But this left-hand side term, fluctuation in the metric, if we adopt the inflation, which is just originated from the inflaton. Again, is in the right-hand side of the Einstein field equation. So, and during the evolution effect is actually all plugged into the here by transfer function. And what we say, and because if you adopt the inflation model, the average is usually is 0, so it doesn't matter. Its meaning is to measure the average value over the observable probable quantity. The thing we need to measure is the Gaussian distribution is just a 2-point correlation function, or in free mode is a power spectrum. So that's why we use that one for the CMB, which is not only for the temperature, but polarization mode, so called as E mode and B mode, which we'll talk about a little bit also today. And also if you apply the correlation function for the matter fluctuation, then it's a large scale structure. And because in the Gaussianity, it means all the linear, and as Jinuk emphasized, in that case, scalar vector and tensor mode is independent to each other. There's no mixing between each decomposition. But if you go to the nonlinear region, in the small scale, there's also mixing in the different modes. So it's complicated. But CMB itself doesn't grow, so that's why CMB itself is the preserve the Gaussianity. Matter is grow, so they actually became a non-Gaussianity in the small scale. That's why they complicated in the small scale, and we need to rely on the simulation in the region. So in the first day, we talk about the background. I talk about the background, and today we talk about the perturbation. And background is nothing but just Einstein field equation with the collision is the Boltzmann equation to delimit the matter part. And for the perturbation, we need to including the collision terms, which is happening between the photon and more focus on the Compton scattering between photon and electrons. And then the perturbation effect is showing in the distribution function over the each component, photon and baryon. And we can see that distortion in the distribution function as a power spectrum. And one thing also wanted to be detailed or the more accurate. When some people say in some textbook they say recombination is not a misnomer because it never been in the combined before. But actually the name of the recombination is coming from the plasma physics. And in plasma physics, when plasma is going to the gas, we say it's the recombination. And gas became plasma is the ionization. So it's a terminology is used in the plasma physics, and so it's not a misnomer. And the first one he used the recombination is the Peebles, I believe, in 1968. And so you'd better to know that it's not a misnomer. It's used in the CMB, and recombination is natural name. So what happened? Before lossless scattering surface, the photon is too hot. And as a Big Bang, as the size of the universe increased, the temperature of the photon is decreased proportional to the scale factor, inverse the scale factor. So as increase the size, the temperature of the photon is decreased. So at the early time, photon is too hot. So no atom can be formed. So all the helium and hydrogen is all ionized due to the high temperature photon. And when the photon coming into the region at the lossless scattering surface, which is Z equal about 10,000, and if you convert it to the calculation T equal T naught with 1 plus Z, which is an inverse scale factor, means if you plug in back to here, that is a 2.7, and it's about 3,000 Kelvin, which means it's only about 0.1 eV. And we know that hydrogen, the ionization is about 13.6 eV. So this energy is much lower than the ionization of the hydrogen. But if you're looking at the counting the number of photon and the number of baryon, you can say electron, then that value is about billion. So that means we have much more. If you photon is not just a single energy, it's distributed by the Einstein-Boson distribution. So even though the mean value of the photon at the time is only 0.1 eV, there's still some tail which have enough photon energy as a 13.6 to ionize a hydrogen. So that's why this last scattering epoch is a little bit lower or older than what we expect. Anyway, so after then, photon temperature is not hot enough, it's cool. So it cannot ionize the hydrogen atom anymore. So it's a form of the atom, hydrogen atom. So then photon just free propagate after from the last scattering surface. So it's sometimes called decoupling, which is a little bit less different from the last recombination. Recombination means just a form of the hydrogen atom. And then decoupling means that now the number of free electron is go down as about 10%. Then lower than this, we say the photon is totally decoupled from the hydrogen atom. So decoupling, sometimes people say decoupling epoch, and recombination epoch has a different name because recombination is right after they started to freely propagate without any interaction. And it depends on how many free electrons we have. And if the number of free electrons is less than 10%, we say it's decoupling epoch. So decoupling epoch is a little bit later than recombination. But you can just ignore it. It's too much detail. But anyway, so last scattering, then it started to propagate. So what we see as a CMB power spectrum is before the last scattering surface, photon and baryon electron is coupled to each other, and it behaves as the oscillation behavior. It cannot grow. So perturbation is have the oscillation behave. And after the last scattering surface, then they just freely propagate to us from the last scattering surface to us. So what you observe is the propagation from last scattering surface to today. Only except nowadays we know that we have the galaxy and cluster is formed. So it's a freely propagate. So it means it's not no information available in here. So it's so-called as dark age in cosmology. But around the Z equal start from the 15 to 6, there's the star forms. So now free electron now is scattered with the electron formed by stars. So this anisotropy generated at the inflation is conserved until here. And that behavior, oscillation behavior was conserved in here. And then it propagate to us. So all the oscillation behavior is actually just located in the last scattering. And that behavior is disappear around the star form after when they're doing the pre-streaming to us. That's the so-called as reionization. And we see those effects today. So let's see that. So as a temperature, we can see the 2.7 Kelvin today is a background temperature, and it's distributed as nicely black body, almost perfect black body radiation. And all the perturbation now we can say in this way. But we need to project that fluctuation on the sphere, two-dimensional sphere projected on the last scattering surface. So it's better to project that as an angular multiple by using the Legendre polynomial, Legendre function. Then this function now based on the Boltzmann equation, we can write in the evolution of the fluctuation, temperature fluctuation in this way. And in free mode, each mode, different mode can have the different behavior. And if we write down this one in the second order differential equation, it looks like the forced harmonic oscillator, as we expect. So oscillation behavior, when we project the Gauss oscillation behavior for different modes, different scale, then we can see the amplitude at the last scattering surface. Eta is a conformal time. Eta asterisk means in the last scattering. So when time is reached to the last scattering surface, black one is a scale as the 0.05 inverse megaparsec, which means about 200 megaparsec size inverse. And then red one is 0.02 K, wave number is 0.02, which is about 50 megaparsec, etc. So the first one is even bigger than the horizon. So it's a super horizon. Then as you expect, super horizon doesn't have any evolution, almost no evolution. It conserves its original shape. When they reach to the last scattering surface, that is almost keep the same form as the same magnitude as the originally generated during the inflation. The red one, which correspond to the about 50 megaparsec, then they evolve, then mode is evolved from the beginning and reach to the maximum value at the last scattering surface. So this one is now after they reach to the maximum peak, then this peak is just preserved until today because oscillation behavior is disappear and it is not happen anymore at the last scattering surface. So if you check the mode at the K or about 0.02, that size is at the last scattering surface is 1 when they normalize to the original, the metric fluctuation, potential fluctuation, as shown in the Ginux talk. This is a metric perturbation at the beginning of the inflation.
Seokcheon, so here the equation for the theta, what is the origin of those equations? Where does this come from?
So it's coming from, so we can express this is a Bose-Einstein distribution for the photon. So photon distributed based on the Bose-Einstein distribution function.
Okay.
So that's so without fluctuation, we can just calculate this one without this term, isn't it?
Mm-hmm.
But now you can use this equation to the Boltzmann equation, collisional Boltzmann equation. So then dTdF, this is a time evolution of the distribution function, including the collision term. This is so-called the Boltzmann equation. So in the photon case, as a collision term, we usually put the Coulomb interaction between the photon and baryon. And this distribution function now have interpreted as a differentiation of the fluctuation. You can obtain from this equation, you can have the background evolution equation, which correspond to the photon number density is conserved as the one equation we have. And the other equation we obtain is this fluctuation equation from the Boltzmann equation. So when you're including the fluctuation effect in the distribution function and adapt the Boltzmann equation, then you can obtain the differential equation, which will be used to calculate these evolutions.
Okay, thank you.
And then,
So it is first order because it is essentially Boltzmann equation.
Exactly, right. So basic thing in Big Bang theory is in the matter part, we should use the adiabatic condition.
Right. So in other words, it's not the dynamical equation, it's just kinematics.
It's kinematic, right, exactly, right. So it's just to use the Boltzmann equation. So it's not a dynamic equation, but just a kinematic equation. And then so if you're looking at of course there's the infinite number of the modes between this one and this one and this one and this one, of course. So some modes is reached to this one and etc. And then some modes is past the quarter oscillation, but look down to the half oscillation. That's the first growth. So smaller region now have the more oscillation and reach to the minimum at the last scattering surface. And then second peak is nothing but they just to the going down to the minimum is a 2/3 oscillation. That's the correspond to the second peak in the CMB, because what we will calculate is we square over this one 2-point correlation function. So the first peak and the second peak is correspond to the first maximum and the first minimum in the oscillation behavior. So that's how in the matter power spectrum, we have this oscillation behavior. But that is a language for the K, and we see that this K can be related to this L, angular power spectrum, angular multipole in the matter power spectrum. They are also related to each other. So that's why we have the acoustic oscillation behavior due to the evolution up to the last scattering surface. And this magnitude is conserved. This just propagate to us from last scattering to us because oscillation behavior is terminated. And another thing is when we observe the temperature fluctuation of the CMB, we are not only measure the temperature fluctuation itself, but it should coming out of the gravitation potential well. If you think the photon was located was the minimum of the potential well of the generated by dark matter, then when they try to coming out of the potential well, then you need to worry, you need to also including that effect. So effective temperature fluctuation is not only the monopole of the fluctuation, but including the gravitation potential. So effective potential is when they're going down into the potential well, then if the gravitational potential is bigger, then when they're going down, it's enhanced the going down. When the potential photon is coming out of the potential well, if this one is bigger, then effective potential is need to overcome the out of the potential well, so the effective potential will be decreased in that region. So you can see whether they're coming from the hot region or the cool region, those mechanisms. So also you need to notice that there's if you measure the CMB power spectrum, there's the odd peaks is always higher than the even peaks. That region is actually that effect is coming from it's a feature of the forced harmony oscillator. So due to the existence of the external potential well created by dark matter, that effect is coming into the F. So F actually gives us the behavior. Odd peak is higher than even peak. And also, there's two main things you need to worry about is if you increase the baryon and increase the dark matter. So if you increase the baryon, that means you effectively increase the mass of the photon and the baryon fluid. This behavior is the fluid of the photon and electron. They are coupled to each other, and it looks like the perfect fluid together. So this behavior is effective mass is if you increase the electron or baryon, then it affects like the increasing the mass. That means you decrease the omega frequency. So if you, in this figure, if you decrease the baryon fiducial mode compared to the fiducial model, let's say omega b, as Stephen say, is about 5% in nowadays. Then
okay, so I have some confusion. Here, the theta zero, that's the second order, is a really dynamics, right? The photon electron couple system, they are under oscillation due to the potential provided by the dark matter, right? Now, in the previous one, you also wrote Boltzmann equation, so which is first order in time. So, and that one is, each mode is independent, right? There is no coupling between different modes. And in the second one, the dynamical evolution equation, that's also, there is no coupling between different modes. Is that right? I'm a little bit confused about how to understand this this oscillating figure and the forced oscillation.
Okay, so this one is without decoupling to the multiple yet. Angular, so K is all different K, okay?
So I can think it's for fixed K or fixed L, maybe, right?
Right, you can say it's a fixed K, okay?
Yes.
And then this zeta itself can be decomposed to the different angular momentum, L, zeta L. So you have the recursion relation. I didn't write down, let me check whether I write down those equation or not, but it's so for the fixed K, you have all different angular modes.
Good.
Recursion relation between the L plus 1 and L minus 1.
Okay.
So now the first picture I show was for the every L, we just think about the different K, okay? So this one is only for different K, which including all the L. Okay? Now, when I write down each step, so all zeta should including all the zero, monopole, dipole, and quadrupole, octopole, etc. We can decompose those zeta as a different angular modes. Okay.
So all the angular modes are included here.
Right. We didn't distinguish that one in this equation.
Okay.
In master equation, we didn't distinguish this part. But those higher modes from the quadrupole is much smaller than monopole and quadrupole due to the K. This one is scaled as K over AH. So those higher multipoles is much smaller than monopole and the dipole.
Okay.
And this monopole is correspond to the density, and this is density fluctuation, and this one is correspond to the velocity, peculiar velocity of a photon. You can interpret it in that way. So this one is also similar to this is so-called as tight approximation, tight coupling approximation, but main effect is coming from the monopole and dipole. And when you consider the polarization, you should including the quadrupole up to quadrupole, which is the source term in here in the right-hand side. That's why we including in here in the right-hand side. But all the higher modules is there, but this is much, much smaller than the effect from up to the quadrupole. So you can just ignore that. But in original equation, as you can see in the later, is all included actually. So after you decompose to the angular momentum, then you can say about those things. All the L modes. Okay.
Okay. And then your dynamical evolution is describing what then?
Described by the first differential equation of the zeta 0 prime is related to the zeta 1 and etc. And zeta 1 prime is also related to the zeta 0 and the also potential term. So if you do the one more time derivative for the monopole, you have the pi zeta 1 prime, and you can replace that term to the here.
I see. Okay.
And you can now have the zeta 0 double prime is related to the those omega square zeta 0 and the source term.
Okay,
and
thank you.
Became a the harmonic oscillator. So you are right. I skipped the because lack of time. I cannot show too much detail. But yeah, after you have all the multiple first order differential equation, you need to do the one more differentiation for the zero monopole to get the second order differential equation. Okay. This one hopefully is okay. So if you increase the barrier, means you decrease the omega. So that shows that effect is showing here. If you decrease the barrier, then that means you decrease the mass, then you increase the omega. So the frequency is decreased, frequency increase. So it have the faster oscillation behavior. You see? And effect of the C is you increasing like the potential, the external force in here. So if you increase that, that effect is now there's a more difference between the even peak, odd peaks and even peaks. So that effect is if you decrease the dark matter, then that differences between the even and odd peaks is increased. So if you measure the height, relative height of between the odd and even peak, you can have the strong power about omega B and omega C, because cosmological parameter, as Stefan said, there's a 6 and 7 or 6, the fundamental cosmological parameter can be obtained from the CMB based on the lambda CDM. Those effects can be degenerate with other 4 parameters, but the relative ratio can have the strong constraint for the omega B and omega C. So that's important. But the problem is, if you go to the small scale, then photon is diffused. So that what happens is, if you have looking at the smaller and smaller scale, that means total distance traveled by those small scale is increased. So due to the lot of the photon diffusion, originally generated the anisotropy is disappear, is washed out. So those the spectrum, originally we have a peak lower even peak and higher and odd and even. But if you look at the reality, then those higher modes have damping because of this photon diffusion. So this is so-called Silk damping or diffusion damping. So small scale is related to the lensing effect, weak lensing effect, which can extract the information of the matter distribution, but that amplitude is washed out. So it's a more second order effect. The original primordial shape is just coming from the first few peaks. So so effect is also the same. If you decrease the baryon omega b, the energy density contrast, which is all used in the interpretation of the observation, that effect means that actually you decrease the baryon number. So baryon number decrease means the increase the omega lambda d, the total co-moving distance. So it makes a stronger damping. That effect also showing in here, but the amplitude in here is much smaller than here. So it's quite difficult to measure and lots of noise, as you can see later. So after loss scattering, now how we can relate to this K mode for the angular scale. We can think about that. So this is the length of the arc. So if we measure the temperature difference between here and here, position 1 and 2, because the average fluctuation in here is 0 and here from here is 0. So it's meaningless. So we always need to check the 2-point correlation between the position 1 and 2. So we measure the angular difference generating coming from different directions with the angle theta. So that wave number, inverse wave number, is just the size of the distance between two positions. Is just the length of the arc. So it's nothing but just for the flat universe is c multiplied by conformal time. So it's just a physical distance, angular diameter distance from us to the last scattering surface. This distance is fixed. It's not changing. So it's just a projection. So the lambda or inverse k is nothing but just theta multiplied by angular diameter distance. And that number is fixed. But, and then in the multiple L, we can approximately relate this one as the inverse theta. Because of actually, if you, that is depend on the detail, but the reason is the L modus is maximally enhanced when the L is the same size as this line. Of course, there's also contribution from the all other JL, but it's a characteristic of the Bessel function. Bessel function have almost the damping when L is different from this variable. So we can relate to the L as the K eta. And so that's why we can relate to that L is nothing but the inverse of the angle, which is related to K. So that doesn't necessarily mean that L is the same number with the K. K including, for the 1K, every L is included. But those specific size is related to the L because due to the behavior of the Bessel function. And then we can characterize that angle, the distance, as the angular multiple L, okay? And which is related to the mode we have. So this traveling distance is fixed, and we measure the angular difference between two positions to show the power spectrum. So it's a freely propagate, except that there's the also generation of the gravitational potential coming from last scattering to the Earth by the clusters and etc. generated by dark energy. Those effect is so-called as an integrated Sauer effect, ISW effect, and also the scattering happen in the star formation around the z equal 10, less than 10. That's so-called as a recombination. And due to that, again, the original form was disappeared due to the the interaction with the free electron around the star. So it's again, it's also damping the anisotropy. So it's a free streaming except two cases. One is the ISW and the ionization. So that these two effects is including the integration for the time. But except that, every form is just fixed at the last scattering surface. So again, we can do the temperature fluctuation projected on the, because we will measure on the two-dimensional sphere. So it's better to decompose this one projected to the spherical harmonics and then showing in the different angle. And those magnitudes is just specify the coefficient of the spherical coordinate harmonic function. And for the power spectrum, we can just assume that it's an ensemble average over the ALM is 0, and the 2-point correlation over the coefficient just give us the angular power spectrum of the CMB anisotropy. And reality is instead of ensemble average, we need to do the spatial average. That's so-called as the cosmic variance, as I mentioned at the first day. And then same thing, we wanna change this one original the power spectrum observed today is related to the metric perturbation generated by the inflation, and everything is just invoked to the transfer function in here. So primordial shape power spectrum generated by inflation, which we use that as AS with K pivot scale with 1 minus NS. Okay. And then this transfer function should be involved in the calculation in here, in the Boltzmann equation. And the integration part is, so there's for the angular, this is the angular perturbation. So for the power spectrum, we just square over this one, zeta L at different, for the different mode. And then contribution is coming from the mainly monopole and dipole and ISW effect. So far we just investigate the monopole and the dipole at the last scattering surface. And then to use the observation today, because we measure the temperature fluctuation power spectrum at today, we need to link this one to the present, the monopole and the dipole, which is coming from this equation by doing the integration. So now we can just calculate the angular power spectrum. Because a photon is a transverse wave, which can have their polarization. So if we put the polarizer and then in the detector, perpendicular to the polarization, there's two polarization. So if you use a stock parameter, we can just use this is a polarization tensor, this is intensity, and then Q and U. And V is for the rotation, but from the Thomson scattering, we cannot have the rotational polarization. So it's all linear polarization. So Q shape is we have the Q as a in the x direction or y direction. If the photon propagates in the z direction. And also U is, we have the XY 45 degree and minus 45 degree rotation in the polarization, that's the U mode. But QU is not convenient to use in the observation. So we combine those Q and U with the rotation. Then we have the helicity 2 shape of the polarization, so-called as E mode and B mode, and usually depend on the curve free. So that's why we call it as E, and this is B, curve free mode is B, but it's not really related to the E electric field and B field, but just we have the combination of U and Q and U to show it's in the observation, what you observe is in this shape of polarization or this shape of polarization or this. So it's more convenient to use the E and B mode. And E mode is coming from the scalar perturbation, also tensor perturbation. B mode is only coming from the tensor perturbation. So that's why in the CMB observation, if we want to measure the information about the gravitational wave generated by the inflation, which give us the, as we say in the first day, it gives us the energy scale in the last scatter and then the inflation. So that's why B mode detection is interesting. But so far, based on WMAT and the Planck, and then also, as you can see, E mode and B mode is smaller than T because it's only coming from the quadruple effect. So this is about 10% of the, compared to the temperature. And this one is only 1% of the temperature fluctuation. So that means the sensitivity of the detector is enhanced, and the Planck cannot reach to the sensitivity to the B mode. It can only measure up to the E mode, same in the WMAP. So in the future plan is, of course, to measure the CMB polarization to study the inflation, which is targeting the B mode. And right, so that's the polarization. And as you can understand, if you have the dipole configuration, then you cannot have the thicker means is hotter. This is cooler. But when they collide to each other electron, it gives us the non-polarized photon. So only way to have the the polarization is we need to have the quadruple structure to obtain the polarization in the CMB. And this is to show how we get the E mode. Okay, and B mode is coming from the shape changing in the space-time, so that generates the generation of the B mode. And another thing is, if you go to the higher L, then there's the gravitational lensing effect. What gravitational lensing do is it mixes the E and B mode. So some measurement in the B mode is coming from the E mode. So if you compare the E mode and B mode, this is a primordial E mode and B mode. They are all smaller, so smaller than temperature, but it's twice smaller. It's a square is that. So E mode is smaller than the temperature scale of that, so it's 1%. But B mode is even smaller. But if you go to the smaller scale, large L, then now due to the lensing effect, which convert the E mode give to the B mode. So that's why B mode, measured B mode should be bigger in the large L. So this one is done. But the problem is, because this sensitivity is now reachable, but the problem is this is not primordial B mode. Primordial B mode generated by gravitational wave is only this blue one. And also, so if you want to study the inflation, that one should focus on the only small l information of B mode. But as you can see, it's actually quite small number. And if also the tensor to scalar ratio is too small, then it's even harder to detect. So it's a matter of the detection. B mode is also the contamination is very complicated. So that's the reality. As a CMB power spectrum, there's the numerical tool. Even though I explained the mechanism, now you can just Boltzmann code solving the Boltzmann equation solver code is available. And there's even more the list is before, but this is the only two main thing left. CMB easy was there, but CMB fast is a Fortran 70 and then it's gone. It's old fashioned. It's recovered by CAM, Fortran 90. It's more well organized. Class is C++. And this is the two main thing. And as also parameter estimation is a Cosmo MC is available. And this is scope is maybe not used anymore. Anyway, this is a real thing, real data. The gray dot, actually, as you can see, is all the real data. And it's very sparse, as you expected. It's not easy observation. This one is already after the data reduction, removing all the contamination and etc. So this is an unbined one. The red one is looks like well fitted is a bined one. By averaging those delta L is maybe 50. I'm not sure. Delta maybe 50. So then it looks like well matched with the observational data at the theoretical expectation. This is TE. The previous one is TT. This one is TE correlation, and this is EE mode. And as you can see, it's all sparse data in the high L. WMAP was actually can reach to about the 800 here in the up to here. This is Planck and have the better resolution. And as you expect in order to investigate the primordial one, we should be looking at the large scale and it go up to 30. And then for the large scale, there's almost no evolution. For the K equal 0.005 modes, there's no evolution at all, almost no evolution at all. So you can see this one is almost no evolution. So that actually measure the initial condition, inflation. In the case, one can ignore the dipole effect. So one can remove this one, then only monopole and the ISW effect is coming in. But this is you can check how tough it is, the measurement, even the difference in the Planck data for the 15 and 18. The difference between 15 and 18 is that there's more data included in the analysis. And for the large scale, if you calculate the power spectrum, we can have the approximate analytic solution. And as you can see, L multiplied by L plus 1 CL is DL. And that is when NS is 1, then that's just a number. It's constant value. So it can check the AS. And that's why also in the plot, usually people use the L multiplied by L plus 1 instead of only CL and call it as a DL to show the almost a flat behavior at the large scale in the small L. And also, as you can expect that this one is the size of in here is multiplied by 10 to the 6 by this factor. So due to the Silk damping, diffusion damping, the real data is very small in the large L. So it's even difficult to see the oscillation behavior. So if after you multiply that one to the 10 to the 6 L square factor, then you can see that visible, almost the same order. But that means real data in the high L is about 10 to the minus 6 smaller than the small L. So it's a really tough region to measure. That's why WMAP cannot measure this real region. Okay, so if you're just including the monopole effect, and this is only one, and the monopole and dipole, this one behave like the cosine function, this is a behave like the sine function, so it's out of phase. So if you add in the dipole, that effect is a little bit enhanced and also shifted a little bit. And if you add the ISW, it enhances in the only large scale in here. And then because of the damping effect in here, so it's almost negligible in the small scale. So now, even though numerical calculation show us that the detail, but we wanna interpret how each cosmological parameter affect to the CMB. So the distance, angular diameter distance, will be depend on the curvature. So in the Euclidean case, it's the diameter distance is straight line, but in open universe, it's a curved one. So the distance is increased. That means for the given k, because we measure the same distance in here. So if dA is decreased, then L should be increased, which means that theta is decreased. So by measuring those distances, one can say about whether the universe is closed or open or flat. So if you increase the omega k is conventionally is a minus sign in here. So positive closed universe has a negative omega k. Negative omega k means they increase the dA is bigger than the flat case. So it's a smaller than flat case. So in this figure is this case. For the open universe, is a positive omega k. So that means the angular diameter distance is bigger than the flat case, Euclidean case. So angular scale L, theta is a decrease, that means L is an increase. So if you decrease omega k compared to the fiducial black one, then it goes to the left-hand side. So the effect of the omega k decreasing the omega k shift to the position of the power spectrum on the smaller L, large angle. Okay, that's how we can obtain the omega k from the power spectrum. I have lack of time, so let me just, okay. Also, AS is actually main distribution is in the large scale. So if you increase the AS, then you can increase the overall shape of the power spectrum. So increasing the AS give us almost all the CL. And also, if you change the spectral index, then it's also happen for the shifting in the L. So if you increase the L, you shift to the CL to the right. Also, optical depth, so-called optical depth related to reionization is coming from the two effects. One is escape from the reionization region effect in here, and the scattering in the inside of that region is here. So if you combine these two to including the reionization, that's this effect. So compared to the original one, this minus the optical depth in here. So if you increase that, then you decrease the overall shape amplitude. So if you increase that, then it goes down compared to the smaller one. That's the overall effect. But as you say before, if you're changing the omega B and omega C, it's a little bit more complication. Changing the omega B, if you increase the omega B, then what happens? It effectively you increase the M, isn't it? If you remember correctly. So it decreases the omega, so it shifts to the power spectrum to the right-hand side. But it also increased the odd number because of that it effectively increasing the mass of the photon. So it actually, when they falling down, it's the same direction as the gravitational potential. So it enhances the order. When they coming out, it's against that amplitude, so that decrease the even shape. So it's increase of omega B means that the gap between the odd and even is getting bigger and bigger, as you can see in here. This is the biggest one effect for the baryon K. And for the C, including the C, you shift to the equivalence epoch. So as Stefan said, if you start from the earlier epoch, then there will be a more growth. So that increase the amplitude. Also, it shifts to the smaller size. That's how you get the dA or psi. And also decreasing the potential differential, so it's a decrease the ISW effect. So it can be shown in the large scale, but it's not seeable in here, isn't it? Anyway, so that's how we can interpret the effect of the cosmological parameter from the CMB. And yeah, I have a lack of time, so let me just briefly mention. Because of the contamination, WMAP have the 5 different frequency observation, remove the observation, the contamination from the different the noise. And then the Planck have the 9 channels for that to remove those things. And it's very tough in here. So gray region is they don't use the data in here. And some people argue that this channel gives a lot of error, but yeah. And the main difference between WMAP and Planck is coming from the detection of this region. It's tough. As you can see, as I told you, this is a 10 to the 4, but this is not actually 10 to the 3. It's a 10 to the -2, isn't it, in the real detection? Because this plot is multiplied by L square from the original value. So it's much tougher. And this was the WMAP 5-year data. And as you can see, it's also very sparse, but they hope to measure the 800. But the thing is, this one preserved the more primordial mechanism. The higher L, including the lensing effect, gravitational lensing, and those things is not completely understood yet. So including the higher L really advantage or not is still arguable. Anyway, so let me just try to finish the matter power spectrum because we're out of time. So I just try to explain based on the Professor Seokcheon Lee's question. So this is a linear region, and BAO effect is only around the 0.5, 1 to 1, 2, because as I told you, it's about 100 megaparsec. So if you convert it to the K, it's about here, 125, and wiggle is here. But main thing is in the simulation is this, the dark matter power spectrum. And BAO is only, this is about 20%, and this is baryon is only 5%. So it's a much smaller effect. So that's the showing as of just a small wiggle in here. And after the non-linearism, this theoretical calculation is not accurate anymore. We should rely on the simulation, and it shows the enhancement in here. But this picture is old-fashioned. So, and also as Sevan already explained, the primordial one is only in here. But the thing in here is that as time goes, there's the growth, which is based on our theoretical model. Bias factor is, we don't know anything about it. But compared to the observation to the theoretical calculation, there's always a gap. Baryon is observation amplitude is higher than the theoretical calculation, dark matter calculation. So we need to put by hand some number, enhance the factor. That's the so-called bias factor. And also the line of the redshift space distortion compared to the line of sight and the proper motion differences. We also have this effect. So it's and then this may give us the chance to distinguish the dark energy and the dark modified gravity. And this picture was actually coming from, it's quite old, 2004, Tegma. So as Stefan told us that this is a high Z effect. So not linear is still conserved. There's a non-linear effect is not showing in here. But this picture is projected at the Z = 0 at today. So this picture is not accurate at all because this one is not Z = 0. All four cluster data, large scale structure data is not calculated Z = 0. In the high Z, it's a 0.1 or 0.2 and or even for the 3 and 4, etc. So non-linear effect is not showing in those observations, and also there's the growth effect should be included. This one is a model dependent. How much matter and baryon. Also in this one, in this case, in this time is based on WMAP. So it's different from what we have today. So it's an old-fashioned picture, and it's also distorted information. But the main message in here is from large scale to the small scale, we have based on one single parameter, lambda CDM parameter 6 parameter, explain most of the observation pretty well. But as you can imagine, pretty well means it's 68%. Okay, it's still amazingly good. I believe 68 in cosmological observation is pretty good. And also luminosity red galaxy and main galaxy, even the bias factor is different. We need a more bias factor in the luminous red galaxy compared to the main galaxy observation. And how much B we should multiply, we don't know. And in order to explain the bias factor, if bias factor is depend on the K, that means it also distort to the information of the BAO wiggle. And when we try to reinterpret the Eisenstein's BAO paper, we ask what's the BK he used, but we didn't get the clear answer, because if one multiplied by K bias factor depend on the K, then you can change the amplitude shape by changing the BK. So it's, every detail is quite complicated. So BAO, this one, even though it's for the, you can just focus on the BAO wiggle as this one. This one is actually to see the massive neutrino effect, but just that degenerate with the BAO. We also just focus on the BAO in here. It's the same idea as the CMB, but showing on the matter power spectrum, but it's a very small, tiny fraction compared to the total. So the reality, real observation for the BAO is still very sparse, as you can see. It's very tough. Large scale observation is always limited. It's difficult to measure the large portion of the universe, so it's difficult. But BAO usually provide us the information about the angular diameter distance, also the Hubble parameter. So that's believed to be nice standard ruler. Okay, so I think that's it. Thank you.
Okay, thank you for the very nice review talk. And maybe we can have questions. So if you have a question, please ask.
I'm sorry, I said.
Okay, if there is
time.
no question, then maybe I can ask one question. And it's actually about this optical depth, and you didn't mention much, but what exactly optical depth means, and what is its effect to distort this CMB spectrum?
So optical depth is the inverse of the mean prepass, isn't it? So before collision, how much distance the photon can travel? That's the definition of the optical depth. So it's due to if you have the stars, okay?
Yep.
Generated in the recent epoch. Push the wrong button. So
yeah.
So that's the definition of the optical depth, that how far the photon can travel without the collision. That's the definition of optical depth. So
that's right.
If during the path from the last scattering to today, there's the star formed around the first star we believe to be formed from here to here, isn't it? Yep. Maximally from 15 and more conservatively at the 6 stars started to form. Then now we believe there's no free electron anymore from the last scattering surface. That's so-called decoupling. Yep. So now around the star, we start to have the free electron. So now the photon is started to collide with the free electron around here. Yes. It's the inverse now. There's a free electron. The photon don't need to be ionized hydrogen. There's already free electron around the star. So they just, even though it's very cool, they started to have the collide. So that actually decreased this is an anisotropy generated in there. But that amplitude is now decreased by this collision. So it became an average temperature again. The fluctuation is because after it's like the thermal equilibrium means sometimes it's a paradox. If you have the thermal equilibrium means it's faster than expansion rate, isn't it? Yep. Yep. And it reaches to in Boltzmann equation, it reaches to the so-called as a Sa equation. And Sa equation in here is a collision term in here. But if you do the calculation, then this term became 0 is the Sa equation, which means the collision is effective enough. Then it's paradoxically say that it's same as the collisionist case. The thermal equilibrium means the collisionist case. Means it's the very best collision. So which means that your temperature fluctuation now, because all the different temperature fluctuation now is interact with the electron, inverse Compton scattering, then that anisotropies disappear and it became a photon have almost the same temperature. That effect is showing in here. So you can interpret that this one is wash out the anisotropy by this factor and became an average value. Average value means the theta is go to almost 0, isn't it? To have the T is same as the average T0. So that due to the inverse Compton scattering, the small tiny anisotropy is washed out due to those collision. So that's the what we do by the optical depth. And even though I didn't show too much detail, but this optical depth dependence in the temperature is showing in the ISW effect. Isn't it? This is different in the polarization. So if we can measure the polarization accurately, then we can also have the information about the optical depth is quite important for the star formation information. And yeah, so it's also important. So this is due to the star generation around the path through the last scattering to today and recent epoch. So that's why it only included in the integration effect in here in the ISW effect.
I see. So this the effect of optical depth is only in the redshift between 6 to 50.
Right. So in the real calculation, we don't know. So in the analysis, usually in the Planck, including Planck, they usually use the step function. So they just put in by hand the tau. They cannot draw the tau evolution. So Z, actually there should be Z dependencies, time dependent in the optical depth.
Yes. Because
a star is not formed instantaneously, but it should be just distributed as a function of Z, but we don't know. So in the Planck analysis, they usually put as a step function at the Z equal at one specific epoch. That's the situation we do right now in the Planck. But more interesting is if we including the more data from the polarization, then yeah, because this one shows us the overall effect is just a decrease of overall amplitude. But if you check in the polarization, it shows the different. So yeah, that including the polarization is more important to get the optical depth.
Okay. Even though we don't have much time, let me ask one last question, because I was reading these papers on CMB spectral distortion, like mu distortion or Y distortion papers. That effects are very high redshift, right? But still there is some optical depth effect, right?
So that's totally different. So we know that the CMB is a perfect black body radiation. Then assume that chemical potential of the photon is 0. But in reality, the observationally, the chemical potential of the photon is about 10 to the minus 5. And so mu distortion means if we assume that if we remove that assumption, mu equals 0, if mu is not 0, but have some available value, then it's before the last scattering. Yes, we shouldn't regard it as a black body radiation, but it's a little bit change from the black body radiation. Then what's the effect in the distortion in the CMB? So that's the so-called as a mu distortion.
That's right. But my question was, because in that kind of mu distortion study, people also consider the effect of coming from this the optical depth, integrated Sackwolf effect, like that.
I'm not quite sure.
Maybe I'm also confused. Maybe I can reach you out maybe later.
Yeah, I'm not sure why they interested in that, because it's before the last scattering.
Yeah.
So I don't know why that included in the reionization. I'm not sure. Okay.
Okay, I will talk to you about it later.
Okay. Yeah, that'll be good.
So because we already over time, so
Right.
let's finish here. And thank you,
Yeah,
thank you for your very nice review.
Okay, thank you.
And okay, then we are at I think it's the end of a morning session. In the afternoon, we will have 2 talks, and I think we will see you in the afternoon. Okay, thank you everyone for joining this morning session.
Okay, thank
Bye.
you.
Yeah.
Bye.